Have you ever wondered why some metals like copper shine in blue-green hues or why uranium glows ominously in sci-fi movies? Welcome to the world of D and F block elements, the heavy-duty players of the periodic table that shape everything from catalytic converters to nuclear reactors. Now, let's understand who they are. Transition elements or D block elements are those in which the last incoming electron goes into the d orbital of the penultimate shell, that's the second last shell. Think of elements like iron, zinc, and copper. On the other hand, inner transition elements, the F block elements, are a special breed. Here, electrons enter the f orbital 2 shells deeper and include the mysterious lanthanides and radioactive actinides. These elements are nestled in the periodic table, bridging the metals and nonmetals, and show off their remarkable chemistry, from variable valencies to brilliant colors and unmatched catalytic activity. Let's now see where they live in the periodic table. As we look at the periodic table, focus your attention on groups 3 to 12. These are your D block elements. They live in the center, like the spine of the periodic table, linking S block elements on the left with P block elements on the right. You'll find them across the 4th to 7th periods. Their general electronic configuration? It's n-1, d raised to the power 1 to 10, followed by ns1 or 2. This means the D subshell gets filled just before the outermost S subshell. Based on the period, they're divided into 4 series, 3D, 4D, 5D, and the elusive 6D, many of which are yet to be studied in detail. These elements are the workhorses of inorganic chemistry, showcasing properties that make them essential for metallurgy, electronics, and catalysis. You can see them shaded distinctly in the central block of the periodic table on screen. Now let's travel below the main periodic table. See those 2 floating rows? That's where the F block elements reside. They don't fit neatly into the standard table, so we tuck them underneath to keep things compact. The top row is the lanthanide series, atomic numbers 58 to 71, beginning right after lanthanum. The bottom row is the actinide series, atomic numbers 90 to 103, starting with actinium. Their general configuration is n-2, F raised to 1 through 14, followed by n-1, D0 or 1, and ns2. Unlike the D block, these elements are known for their intense magnetism, sharp spectral lines, and in the case of actinides, potent radioactivity. You've seen their real-world avatars, lanthanum in camera lenses, europium in TV phosphors, and uranium, the giant, in nuclear reactors. As you glance at the periodic table again, those 2 rows now make a lot more sense, don't they? Let's zoom into the D block. These transition elements are known for their chemical versatility. One standout feature is variable oxidation states, like iron forming both Fe2+ and Fe3+ ions. This is thanks to the similar energy levels of their D and S orbitals. Next, their colored compounds. Ever notice the deep blue of copper sulfate or the green of nickel chloride? That's due to DD electronic transitions where electrons jump between D orbitals, absorbing visible light. Then there's their unmatched catalytic ability. Think of iron in the Haber process or vanadium pentoxide, written as V2O5, in the contact process for making sulfuric acid. These metals also form complex ions, structures where ligands like ammonia or water surround a central metal ion, thanks to available vacant d orbitals. And yes, they often show magnetic properties too, a direct result of unpaired d electrons. These traits make D block elements vital in both fundamental and industrial chemistry. Time to shift our focus to the inner transition elements. The lanthanides, from cerium to lutetium, are chemically quite similar. One hallmark trait is what we call lanthanide contraction, a gradual shrinkage in size across the series due to poor shielding by F electrons. This leads to remarkably stable compounds and influences the chemistry of post-lanthanide elements. Most lanthanides prefer the +3 oxidation state, though +2 and +4 states do appear, especially for cerium and europium. Moving on to actinides, the heavyweights. All of them are radioactive, and their chemistry becomes more complex with variable oxidation states, often ranging from +3 to +6. Elements like uranium and plutonium are the backbone of nuclear power generation. Spectroscopically, these elements exhibit sharp emission lines and are strongly paramagnetic due to unpaired F electrons. Unlike D block, F block elements don't form very stable complexes due to their large ionic sizes and poor orbital overlap, but their unique spectral and magnetic properties are widely used in lighting, imaging, and radiation shielding. Let's now compare our two players, the D block and the F block. The D block elements fill their n-1 d orbitals, while the F block fills the n-2 f orbitals, a deeper and more shielded region of the atom. When it comes to oxidation states, D block elements take the crown with a wide variety. F block, especially lanthanides, tend to stay loyal to the +3 state. In terms of complex formation, D block elements are much more efficient thanks to their smaller size and higher charge density. Radioactivity is another key point. While most D block elements are stable, the actinides of the F block are intensely radioactive. Finally, their applications differ widely. D block elements drive industrial reactions, batteries, and alloys, while F block elements light up your screens, power nuclear subs, and polish your glassware. It's a beautiful contrast of chemistry. Let's quickly recap what we've covered in this session. We started with an introduction to the D and F block elements and learned where they're positioned in the periodic table. We explored their electronic configurations and then dived deep into their properties, from oxidation states and catalytic activity in the D block to radioactivity and magnetic behavior in the F block. We saw real-world applications of these elements, from ammonia synthesis to nuclear reactors. And finally, we compared these two blocks to highlight their contrasting but complementary roles in chemistry. I hope this session helped you appreciate how the periodic table is more than just rows and columns. It's a map to the hidden forces shaping our material world. See you in the next class, where we continue our journey through the incredible world of chemical elements and their reactions.